All right, welcome back for part two of chapter 7. Now we're going to talk about the elements a little bit more in detail. And so we're going to start here with looking at this periodic table. And we see that we've got metals, nonmetals, and metalloids. And if you look at the periodic table, most of the periodic table, metals. A little bit of nonmetals. And then right here in the middle, purple metalloids, also called semi-metals. That's my preferred term. So we're going to say, okay, well, if most elements are metals, what does that mean? And what does it mean to be a nonmetal? All right. So our key things here, some key properties about metals. Metals tend to form cations, and nonmetals tend to form anions. So over here, all these positive charges that are common, these all form positive charges. We're not going to talk about them. These all form negative charges usually. Noble gases don't form anything. And they do say, note hydrogen. It can be +1, it can be -1. This we would call the hydrogen ion. Hydrogen with a negative charge we call the hydride ion, just like fluoride, chloride, bromide, hydride. All right. Well, what about metals? And this is kind of the important part for the AP test. Some of the other stuff in this chapter, in the later bits here, they're not going to ask much about. They're going to say, oh, that's too specific. But they want this stuff. They want to make sure you know that metals tend to be shiny, right? Luster means that it has shine to it. You need to know that they conduct heat and electricity, that they're malleable and ductile, right? So here's a piece of gold foil. You can see it's been hammered flat, and then it's just kind of bent on its own over whatever's propping it up. Except for mercury, they tend to be solids at room temperature. Room temperature is 25 Celsius. You'll see in a minute here there's one that's very close besides mercury. And they tend to have lower ionization energies so that they can form cations more easily. So that's why we say, oh, metals, they're the plus charges. It's because of that low ionization energy. All right. For metal chemistry, just some general stuff they want you to know here in the book. Metal oxides tend to be basic. So here they take a nickel oxide, and when they put some of it into both beakers, the beaker with water didn't do anything, but the beaker with the nitric acid, it reacted, and we get this nice green solution here. The other one is that compounds between metals and nonmetals, well, that's ionic compounds, right? We've talked about that before. Metal plus nonmetal, cation plus anion, ionic compound. All right, nonmetals, on the other hand, are on the right-hand side. They can be solids, liquids, or gases, depending on the element. If they are a solid, they tend to be kind of dull, not very shiny, brittle, easily to break. They don't conduct well at all. And they tend to have larger negative electron affinities, so it's easier for them to gain electrons to form an anion. And so that's why we get anions for nonmetals. All right. The opposite thing that they want for this is they said, okay, metal oxides tend to be basic. Non-metal oxides tend to be acidic. So here they have some bromothiamyl blue. They add in a non-metal oxide. It's carbon dioxide. That's dry ice. And when you put it in there, it turns the indicator yellow to say, hey, this is now an acidic solution. When they say most non-metal oxides are acidic, they mean carbon dioxide, sulfur dioxide, maybe even sulfur trioxide. But some of those compounds, if you notice, it's those same ones we had for the gas evolution reactions back in chapter 4. The ones that, it forms this acid that can split up. Now we're forming the acid and going the opposite way. We're putting the acid together. All right, so here's the nice comparison chart. So metals are shiny, nonmetals not shiny. Metals can be hammered and all. Nonmetals tend to break apart. Good conductors, bad conductors. Basic oxides, acidic oxides, cations, anions. So they're opposites. Great. What about the metalloids, the semi-metals? They're in the middle. They are sort of like metals and sort of like nonmetals, hence the name. Some are semiconductors, right? That's the key thing. They're not great conductors. They're not terrible conductors. They're in the middle. So that's why we use silicon, it's semi-metal, to make computer chips that sometimes conduct and sometimes not, is how we make the chips operate. All right, we're also going to look at some of these group trends, and these are the things that are much less needed for the AP test. But we'll just kind of look at some generic things as we go down the column for each of them to say, like, hey, does this tie into what we knew for Z effective? Is this tie in for what we know about having more and more electron orbitals being used that are farther away from the nucleus? Just to kind of reinforce what we're talking about for that stuff. So alkali metals tend to be soft. I'm not sure if that's actually a knife based on this picture. I'm going to guess that's sodium. Sodium can be cut with a spoon if you put enough force to it. You don't need much. They're not found in nature. As the elements, they have to be found in compounds. So to get the elements themselves, we have to do chemical reactions to separate them, get them back there. We do see that they're conductive. Now, they say, oh yeah, we see luster in there, and that doesn't look too shiny. And so think for a second, why isn't this outer surface shiny? It's kind of shiny right there, but why not here? And then hopefully you thought, well, hey, wait a minute. They're reactive. Maybe that outer surface has already reacted, and it has. So that's something we have to always watch out for. A lot of alkali metals, when we store them in a jar of oil so that the oil keeps the water away, so it doesn't react with that. But as we pull it out to use it and we try to wipe off the oil, sometimes that outer surface can react with humidity in the air, and you get a little bit of a dull coating on the outer surface. All right? But if we look at these properties, okay, we can see that we're adding on an extra energy level every time. So the atomic radius gets bigger every time. Great. The ionization energy, since we're adding in electrons to orbitals farther and farther away, it decreases as we go down the column. Notice here melting point also decreases. That's not because of C effective or anything. That's just because of the size. But here you can see cesium. On a warm summer day, if you get up to about 85 degrees Fahrenheit, cesium will be a liquid. So it's barely a solid here at room temperature. And then you see, yeah, the radius gets bigger, ionization energy gets lower. That's what we want to focus on. The famous one that we're not allowed to do in school because, somebody did it stupidly at some point in some place in the country and now it's banned for Carroll County. They all react with water, so lithium fizzes with water. Sodium, you see flames. Potassium tends to just blow up. Sometimes you'll see chunks of it fly out. And then if you went even further, they get more and more reactive. So reactivity increases as you go down the row. Now, here's one that I don't think the AP test needs you to know this, but in my general chemistry class, actually, maybe it wasn't general chemistry, maybe it was an inorganic chemistry class, but one of my college professors made me memorize these three reactions. So I'm going to present them here and say, maybe hold on to them in your back pocket. Lithium will react with oxygen to make a regular oxide, Li2O. Sodium reacts with oxygen to make a peroxide, so Na2O2. Notice we didn't reduce here because that's the O2 minus 2 ion, peroxide. And then potassium, rubidium, and cesium, they're weird. They form what's called a superoxide, which is O2, but with only a -1 charge, which that hasn't been on any polyatomic list I've ever given you. And you're like, well, what the heck is that? It's just superoxide. It's one of the things that actually can cause damage inside cells. So your cells, if we want to, let's tie in a little bit of advanced biology here. Inside your cells, every cell, there is a protein called superoxide dismutase, whose job is to find any superoxide that forms inside your cells and convert it to peroxide, and then peroxide can be converted to other stuff. But this superoxide, that is a free radical with an unpaired electron. That's what can cause some DNA damage, protein damage, all that. So your body does have a defense mechanism against it, but it's formed when these three elements react with oxygen in the air. So it's a weird oddity. Just, like I said, I had a professor who made me memorize it. Maybe you'll have a professor who makes you memorize it. It is in the book, so here it is. All right, flame test. We can see that as we go. That there is a trend here, red, yellow to purple. Now it kind of flips back around as we go down to rubidium because the energy gaps aren't always in order, right? As some move into the ultraviolet as others are coming in from the infrared. So the color for just the flame, remember, is a combination of different transitions. But you can use that to tell them apart usually. But parking lamps are called sodium lamps a lot of times. That orange-yellow glow that you got is because there is sodium in those lamps that are undergoing transitions, so that's why you get that glow. These lamps are becoming a little less common as more people switch over to LED lamps in parking lots. But yeah, I'm sure you've all seen those kind of yellow-orange glow lights on the highway or in a parking lot. Those are sodium lamps. Same transition going on there. All right, for alkaline earth metals, we're not going to have as much to talk about, but again, following the trends, we get more orbitals used that are farther away. So the radius increases as we go down. The ionization energy decreases as they go down. And alkali metals, they form +2. Beryllium and magnesium don't really react with water unless you force it. Like magnesium needs steam, where it's not just water, it's water and heat energy. But the others will react in water. And it increases as we go down, just like it did for the alkali metals. And that's it for that one. If we move on to group 6, the oxygen group, these are called the chalcogens, but a lot of people don't use that anymore. I like that they just say group 6A. Sounds good. The trick here is, as we look at the periodic table, hey, wait a minute, that stair step of the dividing line between metal or non-metals to semi-metals to metals, it cuts across this group. So you see weird things like the melting point goes up before it goes back down. When we looked at the metals here, right, it was down, 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 down. Usually there's a gap here, but it's usually down, 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 down. But here for the oxygen group, up, 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 down. Well, that's because we're getting less non-metal behavior, more metallic, so that causes the melting point to increase in general. But then as we get even more metallic, well, then it goes back down. But what we can look at again for the normal trends that do hold here, atomic radius increases as we move down, ionization energy decreases as we move down. Again, those are the two trends we really want to focus on. Oxygen being a nonmetal and sulfur being nonmetal, they form the -2 ions. Polonium being a metal would be a plus ion of some type. Probably +4, but they don't even say here because it doesn't even really matter. It's radioactive. We're not going to use it. But yes, and then tellurium's in the middle as the metalloid. Selenium a lot of times is also considered a semi-metal. So here we get some in-between stuff. Oxygen, key thing to remember. In nature, it's usually found as O2, which we should technically call dioxygen, but because that's the vast majority, we just call it oxygen. We also have the ozone allotrope, O3. And then if you just had O by itself, a lot of times we would call that atomic oxygen, just to emphasize, hey, it's just one atom. Sometimes for O2, we'll say diatomic oxygen to say, hey, there's 2 atoms. Just watch out for that. The halogens, they're all P5 for the configuration. Notice here, as they get heavier, now the melting point is going up. So it's the opposite trend compared to the metals. Fluorine, chlorine are gases at room temperature. Bromine's a liquid at room temperature. Bromine is the other element besides mercury that is a liquid at room temperature. And iodine's a solid. So here's the solid iodine there. There's liquid bromine, and then there's chlorine gas. But again, radius goes up, ionization energy goes down. That's what we're looking for. They all form a -1 ion. Noble gases, they all have, well, there's a typo. Argon is not 3s2, 3p2. Everyone real quick fix that. Correct. It is 3s2, 3p6 for argon. I should really check these a little bit better. There's been some typos lately. Again, boiling. They're all gases, so now we're looking at boiling point. Their boiling point keeps going up. All right. So again, like nonmetals, it's as they get heavier, the boiling or melting point increases. Again, the radius increases. The ionization energy decreases as you go down. They make a star here for the radius. It says only the heaviest form chemicals, so the radius for the lighter ones are estimated. So that's why we don't often compare them. When we did the isoelectronic series, we skipped over neon in that group. They did have a table where they were there, and I said I was confused where they got them. Okay, they're estimated. Great, now I know. The electron affinities are positive. They don't want to form anions. They have large ionization energy, so they're not going to tend to form cations unless you really force it. So they tend not to react. They can. The ones down here at the bottom. Xenon has some stable compounds. Krypton has one. There's not really stable compounds for the top three. So they're usually 99.99999% of the time monatomic gases, just neon, just helium. All right, last thing here is hydrogen. They noted that, hey, hydrogen can be special. It's got this 1s1. Is it going to be like the other S1, the alkali metals? And no, not really. So whenever we say the metals, up in that top left corner, hydrogen should not be color-coded like the metals. It can form these +1 ions like in a strong acid, but it's not really an H+. In an acid, it's much more complicated, where this H+ kind of gets connected with a group of water molecules, and it's spread out of where is the extra proton hanging out. So it's not even really an H+ ion like a lithium ion or a sodium ion. And when they're a gas, HCl can be a gas, there it's covalent. So it's not really like an alkali metal, even if we say, hey, it's sort of a +1 ion. Now it can form a negative ion, the hydride, as we said, only with metals. So you can get NaH, sodium hydride, and there it is a negative ion. So even though we put it over on the left-hand side in that first column because it's S1, its properties are much more like the nonmetals or covalent, or where they form covalent. All right, so that's the end of this video. I hope that was helpful. This chapter goes a little bit quicker because there's stuff that the AP test doesn't focus on as much. So I hope you enjoyed that. I hope you enjoyed the lack of mathematics. Chapter 8 continues that trend where there's only a little bit of math and it's pretty simple. It's more descriptive. So finish this stuff up, study your stuff for the upcoming test, and I'll see you soon.